Hello, and thank you for joining us today. We appreciate your attending this much anticipated webinar, our Precision Motion Roundtable, with the editors from Design World and Fluid Power World, which is opening up our Motion Training Days series. Today's webcast is being recorded and it will be available on demand at the Design World website. If you experience issues with your slides or audio, click the information icon in the dock for troubleshooting. Refreshing your browser will solve most audio or video issues, but we also recommend closing other apps and browser tabs. You can also ask for help using the Q&A tool. Now, if you have questions for our panelists, please type those also into the Q&A box at any time. Any audience questions will be answered on a rolling basis after the webinar concludes. The questions will be emailed to our editors for follow-up. And as I mentioned, a recording of this presentation will be available in the coming days at designworldonline.com. I would like to give a big thank you to all of our sponsors for this very first Motion Training Days series webinar: Bokers, PBC Linear, Aerotech, Renishaw, PI, Electrocraft, Novanta, and PhD. My name is Paul Heaney, and I'm the Vice President, Editorial Director for Design World. I've been covering the engineering and manufacturing worlds for more than 25 years. I'm pleased to be your moderator here today, and once again, thank you for joining us. Now, we at Design World receive dozens of engineering updates, press releases, and news items every day detailing advances in and new applications for motion technologies. So I guess our aim here today is to condense and distill all the latest and most interesting technology for you all. Today, I am joined by some of our fantastic editorial staff, and let me briefly introduce them now. Today, we have Rachel Piscini, Editor-in-Chief of Design World, Lisa Eitel, Executive Editor, Mike Santora, Managing Editor, Miles Budimir, Senior Editor, and I'll note Miles is here only on audio today, and then Mary Gannon, the Editor-in-Chief of our sister publication, Fluid Power World. As I mentioned, our staff will be covering kind of the current state of a variety of technologies and systems, including mechatronic solutions to achieve precision motion. We'll also touch a bit on some current motion applications in which precision is really most critical. Now, it is important to note here that the precision motion control we cover relates to discrete automation. And I should mention that precision doesn't really quantify anything, but we use this term, as I would say most in our industry do, as sort of a catch-all term encompassing accuracy, repeatability, and then overall reliability. In this webcast, we're going to look at current technologies in electric motors, including the latest in smart motors and frameless motors as well. We'll cover current technologies in servo pneumatics and precision actuators, encompassing electric motors, such as stepper and servo motors, and rotary to linear mechanical elements, as well as linear bearings. We're going to discuss the latest in precision sensor and feedback options, such as certain encoders, advancing options for tracking position, speed, and acceleration, and then also allowing real-time correction of motion. Controllers have seen some of the most evolution, I would say, in recent years. So we'll talk a little bit about some integrated options for processing feedback input, and commanding precision output. Advanced algorithms include new adaptations of proportional, integral, derivative, or PID loops, as well as model predictive control and advanced motion profiles to minimize vibrations. And then finally, as I said, we're going to consider some specific applications in motion control, especially those in packaging, medical, semiconductor, and other related demanding industries. So let's start a little bit about talking about those applications for precision motion components. I'd like to start with Mike Santora here with one of the more basic components, but one that's still pretty critical. Mike, I know that you cover mechanical couplings a lot. What role are couplings playing in the trend toward, let's say, we talk a lot about electrifying mobile equipment. So maybe couplings and mobile equipment, that's another area our publications write about a great deal. Can you comment on that a little bit?
Yeah, thanks, Paul. Well, first and foremost, thank you for specifying that they are critical I've been saying for years that couplings are my baby. I've been covering them for almost a decade now. They're not the most glamorous of components, but I love them. Even if my wife and kids might think they're sick of hearing me talk about them. But yeah, so there's been quite a push towards advancing the electrification of mobile equipment recently. The electrification of mobile equipment can sometimes cause issues, as you might expect, with misalignment. There's variable load conditions, wear issues, things like that. For those type of applications, people are looking for couplings that can comfortably compensate for angular, axial, and parallel shaft misalignments while keeping side loads to a minimum. This helps extend the life of the electric motors and driven components. But again, with that change to electrified power, there's going to be challenges to integrating mechanical components, performance requirements, dimensional fit up, longevity, other features needed to transition the electric power into the equipment. And that's even more so in retrofit applications. So customization might be required for a proper fit, speed accuracy, and other performance features. I know ZeroMax has a lot of experience with customized solutions for electrification applications. But yeah.
Sorry, jumping in. Mary, you're another editor on staff who I know writes a ton about mobile equipment. Is there anything that you're seeing here with regards to precision motion that you want to jump in on?
Yeah, absolutely. I mean, obviously, hydraulics is probably one of the number one ways that mobile hydraulics or that mobile machines are powered. I think there's a big misnomer, a big misunderstanding that when people hear that machines are being electrified, that hydraulics is going away. It's definitely not. It's too powerful. It's too strong for it to go away anytime soon. And you will find most manufacturers agree with that. So what they're doing is it's been around for a long time. Electrohydraulics is not a new thing. It's been around for a long time. So they're just using a lot more, like you said, controllers. Sensors are obviously huge in this way to make the electrified systems more efficient, but also more precise and reliable. And I think when you kind of talk a little bit about electrified, you kind of talk a lot about the programming. So I think that's really crucial, is that we're really working on these electric systems that are programmable. And leading into that, then you're kind of get into the autonomous machinery, which is still pretty new. It's not as common as electrified battery operated machines, but there are more autonomous developments happening. Danfoss, for example, kind of talked a lot about that at their event last fall that I went to, and I'm actually going to be writing an article about it in our February issue. And I think one of the cool examples that they discussed was how cargo loaders at airports are kind of prone to mistakes and problems because they're human driven. So people are driving these machines up to the doors and they crash. So that's one of the first things that they're automating, because it improves accuracy and it reduces anxiety for the machine operators, because they have this very narrow area of where they're allowed to operate the machine, and that's all very precise. So I think autonomy is where we're going to see a lot of this in the future.
Yeah,
Mary, you're right. Oh, go ahead.
I was just going to jump in and say that, yeah, Mary is absolutely on point. We cover a bit of roller screws paired with electric motors, but every time they're mentioned as a possible replacement for hydraulics, there's always an upper limit, and then it's basically recognized that hydraulics are the gold standard for those high forces.
Yeah, the power density of hydraulics, you're not going to beat that. And I remember early in my career, I mean, Mary, you're right on. I mean, there was this notion of, hydraulics versus electrics, and it's one or the other. But when they said electrics, they meant electric actuation, right? Mm-hmm. And so now we talk about electrification. It's not that same old argument. It's more, how do we use electronics to work together with hydraulics to control it more precisely?
Absolutely.
Let me step back really quickly here. Mike, I want to jump back to couplings, because I just wanted to ask, can you talk a little bit about how the couplings are addressing shaft misalignment in electric motor systems? I know you touched on that a little bit, but I just wanted to clarify that.
Yeah, right. So to combat misalignment in these electric motor systems, you need couplings again, ZeroMax has a composite disc coupling that has high misalignment capability for parallel, angular, and axial misalignments, but can also keep reaction loads low on the connected components. But they also have to have a high torque capacity and high torsional stiffness. The composite disc design does that. And then, of course, for electrical isolation between shafts, all of that helps alleviate downtime costs, maintenance, and loss of production. But also important, for changing to an electrified or partially electrified system, that enables downsizing from a larger combustion engine-driven system while keeping the power necessary for the operating functions. So transitioning to electrified power can be more cost-efficient to operate, besides being cleaner, quieter, non-polluting, safer. Electric motor applications often require uniquely designed shaft couplings for fitting and transitioning electrified power into mobile equipment. Again, that composite disc design can really help with custom shaft coupling needs like that.
Thanks, Mike. What about some other applications? Let me pick on Miles. Miles, I know you've written a lot about this. What about in precision manufacturing, things like encoders, or can you speak on that a little bit?
Sure thing. So when it comes to any talk of precision manufacturing, the key, or one of the key elements, is the sensor that measures the position, and which determines what degree of precision we're actually kind of talking about. And here it is that we can talk about encoders, right? So as we know, encoders are used to measure the angular or linear position of some object or system, such as the rotation of a motor shaft or the position of a linear actuator. Now, when it comes to encoder precision, there are a number of ways that you can measure that. Generally speaking, the relevant metric is accuracy, which is usually measured in arc minutes or arc seconds or even in degrees. And this is basically a measure of the error within the encoder itself. But resolution is the other critical metric too. And that's defined as the number of measuring segments or units in one revolution of an encoder shaft, let's say, or as a measure of some linear scale too. And it's common to measure resolution in pulses per revolution, or PPR, for incremental encoders, and using bits for absolute encoders. So now, when it comes to some recent new products and whatnot, it's safe to say that manufacturers are improving their offerings in several different ways. Two examples. One is from Positol, which recently upgraded the family of its 36 millimeter kit encoders for motion control uses. Specifically, they're using what's called tunneling magnetoresistance, or TMR technology, for more precise measurements of magnetic field changes, which can offer higher resolutions up to 18 bits. So generally speaking, the higher the number of bits, the greater the resolution. And one other example comes from Heidenhain, but from the perspective of networking. And this is their new NDAT3 absolute encoder interface, which has a clock frequency of 200 kilohertz and a bandwidth of 25 megabits per second for faster data transfers. Plus the fact that it's able to reduce cabling benefits a number of different applications, including the CNC machining industry as well.
Yeah, Miles, I've seen you write a fair bit on the CNC equipment side of things. Are there specific advancements or interesting applications there you've seen?
Yeah, sure. So let's talk a little bit about CNC, or computer numeric control. So that's, CNC is not new. It's been around for, decades, really. So just a little bit on that. CNC manufacturing does produce parts with high levels of accuracy and consistency, and typically better surface finishes as well. So it uses software programming to produce parts faster than other manual methods. Typical examples of CNC machines include routing and milling machines, lathes, but also laser cutters that work on steel and plastic and other types of substances there too. So some of the components that make that possible include the sensors and encoders, which we just mentioned. So that's the more measurement side of things. But also hardware is critical there too. So things like the linear motors and actuators that do the actual work, right? And that themselves can be controlled down to those small increments, so that you can get the higher precision that's called for in some of those manufacturing processes. So one example recently is a new CNC machine from a company named Tormac. Their new 1500 MX is a 3-axis servo-driven mill on linear rails with, interestingly enough, an epoxy granite frame for its vibration damping properties. So it features servo motors with absolute encoders that offer 23-bit accuracy with battery backup. So this CNC mill gets rid of the need for machine referencing, and it ensures uninterrupted precision even in between power cycles. One other interesting thing I can kind of mention here in this regard is that one manufacturer of precision ground ball screws, Dynatech, has seen an increased interest in replacing older Acme ball screws with precision ground ball screws when they're refurbishing and upgrading older machine equipment up to modern CNC technology and standards. So some of the benefits there include more precise and repeatable positioning with lower backlash and minimal deadband, associated with the precision ground ball screws. And there's also a benefit in terms of increased efficiency using ball screws that can also then result in smaller size drive motors as well. So,
yeah. Miles, I think that it's interesting that the 3 different encoder examples that you gave really rely more on the software to make the most of what the encoder signals are putting out, and then also the connectivity, right? So they're really traditional encoders that we've known and loved for many decades, but kind of complemented by new tools allowed by, better controls.
Right. Yeah, absolutely.
Thanks for that. Well, let me throw this out to everyone. What else jumps to mind with different industries or good use case scenarios for these types of components? Anyone?
Yeah, sure. I can chime in. There's plenty of interesting aerospace applications. I think that, again, kind of like CNC, these things aren't new, but they're in increasing demand these days, and they follow the trends of miniaturization. There's a lot of light weighting in aerospace, and of course, what we're talking about here is precision control. So specifically, pointing systems are critical in satellites for maintaining the satellite orientation in space, as well as staying fixed on their targets. These systems, they use rotary actuators, sensors, and encoders that Miles mentioned, and various motors, either stepper, brushless, DC, or direct drive, depending upon the design and what they're trying to accomplish. For example, antenna pointing systems, they're used for communication, GPS, deep space exploration, and military surveillance. But for all these applications, the antenna needs to be accurately fixed on its dynamic target. So while the satellite's in orbit and the Earth's constantly rotating, or perhaps there's a target in deep space or on the ground that's also moving, these precision motion components, they're working together and constantly adjusting to maintain that satellite's and antenna position. And what do they estimate? There could be roughly 10,000 satellites orbiting Earth at any given time these days. And I think I've read that number could increase to 20,000 or even 60,000 in the next 5 years. So maybe by 2030, when you look up at the night sky, you see less stars and more satellites orbiting the Earth. But it's, as far as motion components and manufacturing of them, goes, it's likely we'll continue to see more compact, more lightweight, and energy efficient components, specifically for these pointing systems. But there's also antenna pointing systems permanently installed on ground stations, mobile marine vessels, which are subject to harsh weather conditions. They're also on aircraft and mobile ground vehicles, which all require the same accurate positioning and targeting. But for each of these, they contain the same components, but their design considerations are much different. The sizing, mounting, the materials used, definitely maintenance requirements differ based on the environment they're in and the purpose, what they're supposed to be targeting and tracking. So it's interesting in that sense to learn how precision motion systems are assembled and used to control position relative to other motion, either its own orientation from forces acting upon it or even to reliably track another object's motion. I think it's pretty neat.
Anyone else? Mike, anything like semiconductors you could talk about?
Yeah. Sorry, I think I was muted there for a second. Just an interesting application. Just off the top of my head, it's not as interesting as the aerospace application Rachel just talked about. It's brakes. But in our design notes department for print edition of DW last year, we ran an article on a company that's brakes are being used for positioning semiconductor wafers during scare assembly operations, which I think is kind of cool. The process requires instantaneous braking and holding power without introducing too much heat into the system. This company, it's Mickey Poley, their BXR LE brake. It's this compact, slender model that provides tightly controlled braking in a confined area while using minimal power and, of course, without introducing heat into the system. Kind of a cool application.
Awesome. Thank you, Mike. Let's take a quick break from our wonderful live panelists here for a few minutes. I recently chatted with Jim Hammerand, who is the managing editor for our sister publication, Medical Design and Outsourcing, about where precision motion components are used and some of the challenges for them in the medical field. Can we play that video here, please? I'm here today with Jim Hammerand, the managing editor for the publication Medical Design and Outsourcing. Welcome, Jim.
Hey, Paul. Thanks for having me.
Jim, I was hoping you could share with our viewers some of your insights. Could you explain a little bit or describe what are some of the medical devices that your publication covers? And then what are the motion control components that you would most commonly see when you're dealing with those specific devices?
Sure, I'd be happy to. So if it's a medical device that falls under FDA regulation, we cover it. That includes products like the very simple swabs that doctors use to collect samples for a COVID test or a flu test, or devices like IV bags or surgical scalpels or sutures, but also more complex devices and systems like pacemakers, brain implants, and these catheters that can go into your blood vessels to remove clots or deliver energy to treat high blood pressure or atrial fibrillation. So as far as the medical devices that have motion control systems, we're talking about imaging systems like MRIs and CT scanners, things like prosthetic hands. And then there's very exciting field right now that's medical robots. So right now, those robotic systems are mainly focused on robotic assisted procedures that were traditionally performed laparoscopically or for major replacements of joints like the hips and knees. But we're also seeing robots in development or that are already FDA approved for biopsies deep in the lungs and for complicated procedures like heart valve replacements. So lots of motion control sensors and encoders, motors and drives, actuators and springs, those sorts of components. I should also mention pumps, but not really pumps for hydraulic systems. These are more pumps for drug delivery, like the automated insulin pumps that diabetes patients wear to manage their condition, or pumps for dialysis, or even heart pumps. So these can be external machines that keep a patient's blood flowing while they're having open heart surgery, but also implantable cardiac pumps that keep heart failure patients alive while they wait for a heart transplant.
Oh, really fascinating. Thank you for that, Jim. I'm curious, what are some of the unique challenges you might come across with medical devices that an engineer would come across when specifying precision motion components?
Yeah. So reliability and durability are more important than ever with these life or death situations, right? So I just mentioned implantable heart pumps. We interviewed one patient who had a heart pump implant keeping him alive for 7 years while he waited for a heart transplant. So you want to minimize, obviously, how often an implanted device like that needs repair or replacement. Either way, you've got to open up that patient for a pretty risky procedure. Power management is another important consideration for any sort of wearable or implanted device with motion control systems. And a huge trend in medtech right now is miniaturization. That's making possible all sorts of minimally invasive procedures that help doctors and surgeons treat patients more effectively or as effectively while reducing the risk of complications and shortening recovery times. So with the motor control systems and surgical robotic systems, for example, you need precision and accuracy, minimal heat and vibration, and you need smaller motors. A lot of these systems have the motors outside of the patient and use pulleys or artificial tendons to move the instruments once they're inside the patient. But some of these motors are so small, they actually fit inside those robotic instruments and inside a patient's body. And then even outside of surgical robotics, there's one company we've been covering that has a motorized camera robot, and it's so small you swallow it and it swims around your stomach to investigate GI problems. And this is something that you could swallow at home while a doctor controls it virtually. So that's another big trend in medtech, the shift of care from clinics and hospitals to the patient's home. So there are now dialysis machines that patients can use at home instead of visiting a clinic. So engineers need to consider whether the motion control systems they pick can not only withstand that home environment, but fit into the new environment with minimal disruption and easy operation.
Sure. Yeah, some of that's straight out of sci-fi. Amazing, Jim. And then just one last question for you. I assume that regulations are a pretty big part of your world. So designing a product that is going to be put into the body, permanently, like a device, or temporarily, if it's a robotic surgery arm reaching in there, that's a far cry from designing a product in, the mining industry, a packaging industry. Can you speak to that and how that affects products a little bit?
Yeah, that's definitely a big difference. It might be the biggest difference for medtech engineers. So before a device developer can get the FDA's approval or authorization to sell their products, they need to go through extensive verification and validation to ensure their products are safe and effective. So, again, that goes back to the reliability and durability that we talked about. But one big difference is that medtech manufacturers have to demonstrate biocompatibility for any of their products that come into contact with a patient's body. So obviously regulators are not going to allow a product that leaves hydraulic fluid on a patient's skin or in their bloodstream. But even beyond biocompatibility, to avoid the risk of infection, medical devices need to be sterile when they get to the doctor and the patient. That's another part of the regulatory process. And so every year, around 40 billion devices, that's billion with a B, in the U.S. are sterilized with different methods like heat or gas or radiation before they're shipped to doctors and clinics. So those devices and their motion control systems need to withstand that sterilization process. And then there's a ton of documentation required in the development and manufacturing stages. So device developers can not only prove to the regulators that their products are safe enough for use, but also so they can identify and fix a problem if reports start coming in about defects or malfunctions, whether products just aren't working as intended, or in the worst case, if they're causing serious injury or death. So all that V&V and paperwork can be a huge headache for device developers, but with lives on the line, there's no way around it really. And when you talk with medtech engineers, the big payoff for them after all that work is bringing a product to market and seeing how it can improve for safe lives across the globe. For
sure. Jim, thank you so much for sharing your knowledge here. Can you provide the MD&O website URL for our viewers in case they want to dig into this particular topic a little more?
Of course, yeah, we're covering this a lot. This is medicaldesignandoutsourcing.com. You can go to find us online. You can subscribe to our newsletter, and then follow us on LinkedIn as well, where you can get a lot of more real-time updates from myself and other editors at MDO.
All right. Thanks again, Jim.
Thanks, Paul.
All right. That was really interesting, and I do encourage you all to follow Jim and his whole editorial staff on MD&O. They're always covering really fascinating innovations that engineers are creating across the medical fields. Do any of our editors here have any additional thoughts on medical applications?
I do know that Miles just edited a piece on the autoclavable medical tools, right? And it's interesting how it's really standardized on, for sure, brushless DC motors, like almost as a rule. But specifically that there's a decision to be made between slotless motors versus slotted motors, with slotless motors being, maybe more delicate and need to be integrated a little bit more carefully, but offering benefits of compactness and lightweight and all the rest. I think where Jim mentioned the implantable pumps, it's almost certain that what he's talking about for the electric motor are, again, brushless motors. And these are gear motors. And I won't name the manufacturer. I think there are a couple manufacturers who offer this, but really it's not the motor that's special. In this case, it's more the gearing that is ceramic. It's teeny, teeny, tiny, unbelievably tiny little gears. And they are made of ceramic that is injection molded, right? So they're, among the most precise gears in the world.
Thanks, Lisa. Mary, Jim was happy to throw hydraulics under the bus. I'm sure you have some sort of a response.
I laugh that he referenced it twice, because that would be horrifying if anyone tried to use a hydraulic pump in a medical device, because the fluid is not compatible with a human body. And we have lots of experts in the industry that would talk about the dangers of hydraulic fluids near the human body. So we won't go there. For sure, the other side of fluid power definitely plays big into the medical device space, the pneumatic side. And we see a lot of pneumatic actuation in medical devices. Sometimes it's not really the traditional sense that we're speaking of, but you probably wouldn't, go into a hospital room without seeing a compressed air line, an airline for use on a lot of devices and things like that are helping people keep safe and alive. Air is clean and it's easily available, so that's why it has a great advantage for use in a lot of devices. Lisa, you kind of mentioned the miniature devices that are used in these pumps. I don't think they're using air motors in, those little things that are going into your mouth and you're traveling through your bloodstream. But air motors and air valves are critical for a lot of medical devices, and they are usually very small. Clippard comes to mind as a company that kind of innovated and made that sort of a gold standard in the industry. They kind of started in the industrial automation side with their little cylinders, and now they're completely in the medical side. And they continue to come out with unique valve designs. But, the thing about all fluid power and pneumatics is it's very snappy. It is very precise if you control it the right way. And it is very compact. That's why you're going to see, compressed air in a dental office pretty much every time you go in there. So no hydraulics, but pneumatics, it's all over the place.
And you said air is clean. Non-lubricated air is clean.
Yes, yeah.
Always have to remember that. Anyone else here on the medical side? Any other thoughts, or should we move on? All right, I guess we'll move on. Let's talk, since we got Mary speaking up here, let's talk a little bit about electromechanical versus pneumatics, maybe Mary and Lisa, where each of those two technologies has its ideal place. And I know, Mary, you were even on a recent, I think, a Festo call on servo pneumatics. Do you want to start?
Yeah, sure. I mean, Lisa was on that call as well, and I know that she was kind of fascinated, as I was, by some of the newer technologies they were talking about. They released a lot of new valve technologies to the U.S. market for its, as they call it, its precision pneumatics offerings. One of the things that they talked a lot about, and they wrote an article for us at Fluid Power World last August, was controlled pneumatics versus servo pneumatics. Pneumatics is precise as it is, but then once you get into servo pneumatics, you have a higher level of precision. And now they're using a piezo valve that helps them to even get further into the precision and the programming to allow it to be reduce energy consumption, control leaks, control flow and pressure rates a lot easier than you would with standard pneumatics. I know that there's a lot of concern about efficiency with compressed air. And Paul, you post about that a lot with our series from Ron Marshall. But as Ron Marshall points out in every article he writes for us, there are so many tools you can use, advanced flow controls and regulators from all the major companies, modern programming. Miles talked about sensors, IoT. If you take advantage of all these powerful, cost-effective technologies, pneumatics is still so viable. Companies like Festo, obviously, Norgren, Proportion Air, any of those companies, they are constantly innovating to continue to make their technologies as efficient as possible. But most of the stuff they're releasing nowadays is electro-pneumatic. And so it's just like above when we were talking earlier about the electrohydraulics. There's not going to be probably much systems that aren't using that combination to really keep the operations functions running as efficiently and precise as possible.
Yeah. Yeah. Mary, I think it's telling that all of these the suppliers that you mentioned all offer pneumatics as well as electric motor solutions. Mm-hmm. And yeah, it's for sure unbeatable, right? The electric motors can be exceptionally efficient. But on that call, I felt like a little bit of an, interloper on the pneumatic side. I don't get to cover it a whole lot. I thought it was really cool, right? That manufacturer sells all kinds of electric motor systems, components, you name it. But there were a few applications that were ridiculous to do with electric motors. They mentioned metering, pressing applications, blowing applications. And then I think the most fascinating to me, like a 3D sanding application where you needed, this application needs the coordination of in real time, right? Like this sort of soft sanding pad to contour over extremely complicated geometry. And it's possible to do that with electric motors, but the direct interface, I guess, of the pneumatics with this sanding end effector just is so clearly, it's so intuitively the correct solution. So I think some of the applications you talked about there too, like I think safety comes into play, like electrical can't be used in certain things. So obviously, where the power and the precision that electrical is, maybe pneumatics might be better just because of the safety issues. Yeah. Yeah.
All right, let's chat some more about other applications. Where else are you editors seeing any interesting new use cases? Anyone, throw it out to the whole crowd.
Yeah, I can volunteer another one. I know just kind of inspired by Mike was talking about semiconductors, which I disagree was a very interesting discussion there. So thank you for adding that. But to piggyback on that, kind of another angle of semiconductor manufacturing, with everything getting smaller and the whole trend of miniaturization, Jim mentioned and Mary and Lisa are touching upon, to manufacture such small semiconductors, you need these devices and these systems that can work at that miniature scale. So nano positioning systems, are very critical for this. And they're used in various places in the manufacturing process. They're used for fabricating the wafers, handling and inspecting them. They're used for packaging, and they can be used for other processes as well. And they're not new. I think they started maybe like the 80s, early 80s or so, but that was in a time when electronics were bulkier. Computers were bigger, things were designed larger than they are today. So there really wasn't a need to refine this technology. Since then, it's evolved quite a bit thanks to a lot of this precision motion technology and all the components and the refinements we've been talking about so far. These systems, the nano positioning systems, they typically consist of piezoelectric actuators and stages that are designed to be frictionless and vibrationless for that exact, quick motion to ensure that nanometer precision and positioning. And they're also very fast in that case, which is great because of this increasing demand in quantity for semiconductors and electronic components. So there's a push also for designing more lightweight stages, but without compromising the control that they have to keep up with such demands, also as far as quality goes, not just quantity. And in terms of control, digital controls are certainly more preferred over the traditional analog controls in modern systems. And they increasingly integrate AI algorithms, advanced machine learning programs, to help improve the performance, to refine that precision based on real-time data they're receiving in order to reduce any errors, and also to maintain the components in the machine to eliminate downtime or prevent wear, or at least slow down wear of these components. Another really cool concept that you might read about is applying magnetic levitation to nano positioning systems. This technology uses magnets on linear stages to create magnetic fields that provide frictionless motion and contactless motion, which can improve the precision, still reduce wear, and also reduce the particulate contamination during production, which is really important for semiconductor and other clean room type of applications. For example, PI developed the PI Mag 6D. It's an electromagnetic positioning system. It's controlled by a 6 degrees of freedom sensor. And they have some videos online, and they're putting a lot of research, investments into that technology. So we should see more developments of that in the coming years.
Yeah, I'm going to chime in too again here, Rachel, because I was just thinking about the semiconductor application that I mentioned before, and you touched on this too. Cycle time is obviously critical in semiconductor assembly, and that BXR-LE's braking response and holding power makes it work for high-speed applications. It's a power-off engaged brake that holds a semiconductor wafer in place. For the subsequent operations, the brake is energized, which disengages the rotor disc for the next assembly operation. Because these semiconductor assembly operations are fully automated for long-term operation, maintenance-free braking is really important for their uninterrupted operation. And that's why those brakes excel for semiconductor assembly, but also for applications like biomed or packaging applications as well. So I thought that was kind of interesting.
All right, I can chime in here too. Maybe while this is not exactly an application, but it's more, I think, of a sort of telling example of kind of how all these trends are kind of coming together. And this is basically a stepper motor drive with closed loop position control, which gets you servo-like versatility, precision, and repeatability in a stepper motor drive, basically. And this specific drive that I'm talking about is from Cole Morgan, and it has a really neat feature that kind of helps track a load position via encoder feedback, and then automatically corrects for any overshoot or undershoot error in the system. So this is handy because it can aid in minimizing scrap, right, and also kind of stop any damage, basically, right, from kind of happening to the system itself. And so it's really helpful for applications which have simple point-to-point movements as well as linked motion sequences, such as, to tie it back, such as in many CNC manufacturing uses and processes, basically. So.
All right, thanks, Miles. I feel like no discussion about technology today can really happen anymore without at least a cursory mention of AI and how it is affecting everything in the world today. Anyone here have thoughts on AI and motion applications?
Well, since I mentioned it just a minute ago, I'll go ahead. I'll take that one. You guys can chime in if you have any other comments too. But you're right. I mean, even though we're talking about motion, we got to talk about AI. It's being leveraged and integrated more and more in every industry and all sorts of different equipment. So engineers need to be better acquainted with it. And they need to understand how AI, machine learning, first of all, what they mean, and even quantum computing and how these technologies influence advancements, influence their jobs and the systems that they build, and then how people will use them, how they're built for the design and built for the operators. So one of the main draws for AI these days, aside from the fabulous chat GPT capabilities that give people all the knowledge that they need at their fingertips, the big thing as far as motion control components and machines is the predictive maintenance capabilities. So the draw is to collect real-time data and make decisions on the spot so that systems can automatically adapt to changes in the environment. Temperature changes, pressure changes, anything like that. And they can adjust and prevent or slow the wear of the components, the equipment. They can optimize energy usage. They can stay within their, peak operating ranges, correct errors, all without human intervention. So you don't have to have somebody sitting there constantly tweaking a machine all the time or being reactive to a change. And you can reserve humans for more critical or creative thinking tasks. So this ongoing optimization, it can obviously save time, it can save money and maintenance, it can improve performance. all which can increase productivity, throughput, efficiency, and so on. So that's, one of the big draws and kind of the dreams that I think everybody's really trying to work for in these early developments of applying AI to various components and systems. And one thing you might hear when you're reading about new products is there'll be these self-learning or self-teaching components, which basically means that there's an algorithm that continuously receives data from sensors, it's making adjustments, and then it receives feedback on the adjustments that it's made. And then it'll refine itself to meet specific requirements. So that's kind of the self-learning, that receiving feedback on its own changes and making adjustments to, meet the program specifications. It's a really rudimentary description. It's way more complex than that. But the idea is not only to make a system more productive or efficient, but it could also be used to improve safety. We've touched on safety here already, medical devices, but also in robotics applications. Mary, you talked about pneumatics and safety. In terms of material handling, it can take multiple data sources simultaneously and quickly compute the best output in given conditions, really applicable for AMRs or AGVs, the automatic vehicles that are running around warehouses, for instance, or robotic arms that are used for surgeries. So it can improve precision, in those critical medical applications where robotic arms are being more widespread. But of course, it always sounds wonderful. We think of AIs as, I call it a magical watering hole for all data to come and congregate so that all can flourish and everything can be improved. But, of course, there's challenges. And, the classic saying, garbage in, garbage out, definitely applies here. So, if incoming data is latent, if it's inconsistent or inaccurate, no matter how sophisticated your algorithms are, the output is likely to be inaccurate. The models of the world and the maps that they create, they're likely to be imperfect. So these adjustments will be delayed or imperfect depending upon the quality and the timeliness of the data received and processed. And the algorithms also require a lot of data to perform this in an ideal manner. It's not something you can just plug in. You kind of have to wait. You have to feed it good data over time. So it's a very data heavy and therefore energy intensive process. And I think that's something that people, especially when we're talking about maybe digital transformation as far as, machine building and overall processes and system control goes, it's not just about having these AI algorithms or the intelligent components. It's also about having reliable sensors, that network connectivity. Lisa, you mentioned that too. Interoperability, all the necessary hardware and software. So the companies that are making these huge investments and dedicating time to develop and implementing AI integrated solutions, they're really leading the way for everybody. So eventually it can be, more user friendly and more cost effective down the road, possibly.
Yeah. Rachel, I think maybe you did some editing on this piece too. It was from our friend Boaz, who is a researcher. So kind of at the opposite end of the spectrum of investment. He's working on some exoskeleton therapy exoskeletons, as well as mobility assist exoskeletons, like bleeding edge stuff. I don't mean literally, but it's really cool design, right? And it's using AI at the research level. So like probably pretty small budget, but I think we put this in the last Design World casebook. So they they basically applied machine learning AI to the controller, and they are gathering gyrometer position feedback as well as force feedback to sort of in real time model how these exoskeletons should feel or improve how they feel, I guess, make them more comfortable. And it kind of, and sometimes it is a conflicting design objective, right? So what's more comfortable might not be as powerful or fast, right? So there's this competition, there's a conflicting design objectives, all while trying to make sure that these designs stay safe. So yeah, TBD, it's not a commercially available exoskeleton that they were working on, but being worked on with iterations of AI. There's another example one of the new motor designs that has come to market is a printed stator motor. And a lot of those, there are a couple couple offerings in that space now. And that is the kind of motor that is now being developed using tools of AI to just crank through many motor design iterations to optimize for specific applications. For traditional motors, we don't hear too much about that yet, but for these more exotic motors, we're definitely seeing it.
Lisa, that makes me think we did promise to talk a little more about motors. Any other new developments in the design of motors that you've seen, or was that pretty much the highlight?
I mean, yeah, for sure. Those, their axial flux motors are increasingly common, especially for things that need to be compact in AGVs and those kinds of applications. And then kind of in the same vein, and sometimes they're both frameless motors have seen new iterations and, burgeoning applications. Just we hear of new applications every day. What else? There are some really weird motors. I shouldn't say weird, but maybe more exotic motors that we covered in the trends issue of Design World in March. Electrostatic motors are now being used in more process applications, yes, but we're seeing on very small scale designs, brand new electrostatic motor designs being introduced to market. And I think, what else? Universal drives for driving any kind of motor you have, right? They're a new breed of drives that can, connect. It can give that power to brushless motors and stepper motors, brush motors. And those are, I think, again, just introduced to market because of the increased power efficiencies of today's electronics, power electronics, and the smarts that can be squished into ever smaller drives.
Great. Thank you. All right. We have one more special guest star I would like to introduce here. I also chatted last week with Mike Oitzman, one of our editors with the Robot Report, on some of the fascinating innovations he and his colleagues are seeing with precision motion components. I think you all will really enjoy what Mike had to say. So can we play that second video now? I'm here with Mike Oitzman, the senior editor for the publication The Robot Report, which is a sister publication of Design World. Thanks for joining me today, Mike.
Hi, Paul. Thanks for having me.
Mike, I was hoping you could explain a little bit, what are some of the types of robots that your publication covers? And then what are the motion control components that you would most commonly see when you're dealing with these types of robots?
Sure. So at the Robot Report, we cover any kind of robots, basically any kind of robot, but consumer robots. So that's really, anything that would be in a manufacturing floor from a robotics perspective, a warehouse, a logistics hub. We cover delivery robots, autonomous vehicles, construction robotics, robots and drones for inspection, security. We cover healthcare. And agriculture. Basically, our audience is design engineers who are building robots, and we provide all the news and information about new product announcements, including the robots themselves. But we also cover product announcements and interesting stories about the things that make up robots. And so I define a robot as any machine that can sense, think, and act. That's sort of a classic definition of a robot. And, to sense the world, robots need sensors. So we cover all kinds of sensors, simple sensors like limit switches, encoders, proximity sensors, and complex sensors like LiDAR, vision camera, and other types of exotic sensors that are on the cutting edge now. And robots that are able to perceive the world around them use that sensor data and combine it or fuse it into information that gives them a picture of the world around them or a map of the world around them that they can use to make decisions about, what's going on. And, then maybe pick up something, drop something off, weld or paint or sand a surface or assemble a component. So those are the types of things that the robots are doing. And also, to think the robot needs computing. And so we talk a lot about the edge compute that robots are using today. And, edge computing has evolved so much in the last 2 decades, Paul. And this has made things like mobile robots possible. I founded the Mobile Robot Guide back in 2018. WTWH acquired that publication, and now we've integrated that content, into the robot report.
Sure.
And our new publication with the automated warehouse. So, mobile robotics is sort of the pinnacle now of what's possible with, mobile technology. And there, think about all of the things that go into a mobile robot that have emerged in the last 10 years. Battery chemistry has evolved now to make the power possible for these systems to operate a full work shift, delivering things around the warehouse or around the manufacturing floor or even on the sidewalks for delivery robots. And we've gotten that technology from technologies adjacent to markets like autonomous vehicles. So we do also cover autonomous vehicles quite a bit because, again, that's sort of the bleeding edge for where a lot of this technology is being commercialized and made available for the robotics industry. And then even edge compute, what's happening with companies like NVIDIA and others that are making small computers possible to be embedded into these, mobile robot systems. So those are all the things we cover. And then also actuators, motors, hydraulics a bit, power electronics a bit. Publications like Design World go a little bit deeper into some of those things, but we talk about, how those things get built into a system and how they're used.
Yeah, it's amazing the breadth and scope of what you cover every year has to grow as robotics grows.
Exactly. Yeah.
Mike, what would you say are some of the unique challenges with robots, with mobile robots, that engineers are going to face if they're specifying precision motion components?
I think I hit on just one of those to begin with, which is the miniaturization of a lot of this technology to bring edge compute down now to processors that can fit and operate on mobile robots. Again, a lot of this has evolved from laptops, right, over the years. Although robots, are a lot more difficult in operating environment than a laptop is, even in terms of abuse. Think about mobile robots bouncing all day, vibrations, all those types of things that engineers have to consider when they put a system together to move something around. So power consumption on a mobile robot is absolutely critical, just like you would have with a satellite or space robot, something that's has to operate on under its own. So power allocation to motors, to amplifiers, to all of the system components, to all the sensors that I just described. You've got to consider how all of those things come together. And then if you're going to move something, again, being very precise about motion, because again, gear trains need to be precise. Encoders need to be put at the right place in the gear train so that you can get information about how far something moves when you command it to move something. It's a really highly complex system made up of multiple electronics and mechanical components, and then of course the software that makes it all work. So power consumption is key, size is key, but then let's not forget robustness, reliability. Because these systems have to operate, for long periods of time. Customers expect in a manufacturing or logistics environment that these things are going to work 2-3 shifts a day, 365 days a year in many cases. So being able to have a long operating cycle, and then also being able to be designed and built for maintainability is the other part that's important in designing, precision motion, is that, when is it going to wear out? And when it does wear out, how are you going to know, and how are you going to predict that? And then how are you going to repair and fix it in the field?
Sure, for sure. Great thoughts, Mike. Maybe we could wrap up with just a little bit about safety. Especially when there's a robot that's going to be interacting with humans. I assume safety is a pretty huge deal in robotics. So designing a product that moves very precisely, but with those safeguards, has to be a challenge too. And maybe you could talk about that just a bit.
Sure. I mean, safety is job one. We would like to say in robotics, to quote another famous automotive manufacturer. And I started my career teaching technicians how to program, install, and repair robots 3 decades ago. And that's evolved quite a bit from industrial robots of yore, where the robots were isolated in fences and humans weren't in their workspace. And 20 years ago now, it's been 20 years since collaborative robotics became a thing. The idea that you could put a robot next to a human and that it could have the right sensing and the right perception and the right interaction with force feedback and other types of technologies to know when the robot contacts something, whether it's a human or a component or something, to stop the servo cycle in real time. And because real time is what happens with robots, they're operating in real time. You got to be able to understand what's going on and shut it down so that you limit any damage, whether that's to a human or to a component or whatever you're assembling. But things have evolved so far now that the pinnacle, I would say today, is what we're seeing happen with humanoid robots. A lot of conversation that we've had this last year. Humanoid robots are at the top of the hype cycle in terms of robotics today because of everything we just talked about. From a mobile robot that actually can potentially walk around the environment, and the editorial team at the Robot Report were pretty skeptical that these things are going to be in your home anytime soon, just because of safety. The last thing you want is 180 pounds of metal falling on your pet, your toddler, or your grandparent in the home and trapping them or injuring them, right? So not only do the systems have to be designed to be safe, but we need the safety standards and the risk assessment procedures to understand when they're safe and how to put them into an environment where they're going to interact with people. And I still think we're quite a ways away from that becoming a reality, but certainly it will become a reality at some point in the future. And safety always has to be at the key of what, a roboticist or a robotic engineer and a design engineer has to be thinking about with these types of systems.
Makes a lot of sense. Mike, I really appreciate you sharing your insights here. For viewers who are impressed by all your answers here today, how can they stay in touch with the Robot Report and read more about what you're writing on a daily basis?
Yeah, please come visit us at therobotreport.com. And if you're on the podcast, be sure to catch our weekly podcast episode anywhere you get your podcast at the Robot Report podcast.
Thanks again, Mike. All right, we've got to wrap up pretty soon here, but any quick thoughts on what Mike had to say about the robotic type innovations?
Mike mentioned hydraulics briefly, that they cover that a little bit. And one really cool application I think Rachel could kind of just touch on real quickly was a UAV made by Flowcopter. And it used hydraulics because that was really the only option. So maybe you could just give us a quick description of what it is, Rachel.
Yeah, for sure. I mean, it doesn't warrant a quick description, so I actually refer you to the website, to fluidpowerworld.com, honestly, to read more, because we're covering it closely. But Flowcopter, they have a really cool origin story where the owners, the founders, developed a digital displacement technology over at Edinburgh at Artemis Intelligent Power, which Danfoss acquired in 2021. And they've since reapplied that technology and got a patent for aerospace propulsion. They've created a new UAV, which is something that sits between like a drone and a helicopter. And a few months ago, they just announced that they've completed their trials carrying a 100-kilogram payload for 100 kilometers with this device that is not an all-electric UAV. There's hydraulics on board, which makes it a lot more cost-effective option. And their intention is to use it for humanitarian aid efforts and logistics and agricultural applications. So it's a really exciting development. I really encourage you to go on the website and learn more about it and follow them on LinkedIn as well. We'll be giving some updates on there, and they post some really cool videos of it flying around.
Thanks, Rachel. All right, well, I think that's it for today. We're past the 1 hour mark. Once again, if you have questions that you've typed into the Q&A box, those will be answered on a rolling basis in the coming weeks. I'd like to give a big thank you to everyone for attending this webinar from Design World, and for all of our sponsors for this first Motion Training Days series. Thank you so much to all of my fantastic editors here who have just given us such great thoughts and great feedback and great insights. A recording of this presentation will be available in the coming days, as I mentioned earlier, at designworldonline.com. Thanks again for all of you answering our questions, presenting such a fantastic roundtable today. Thanks for attending. Have a great rest of your day, everyone. Goodbye.